So yeah, Yusuf, I think you sent me this, right?
2016, Taiwan. Yeah.
Yes.
Yeah, this one, I've sent you this one. And I think this one was proposed by Ivan Chen, I think.
Yeah. Yeah, I think he created it. So
Yeah.
hopefully it'll be a little harder. So we have a semicircle, diameter AB. So we have A, X, Y, Z. So they're all in that order. So X, Y, and Z are like 3 points. X, Y, Z. I'm going to make Y so it doesn't look like it's the midpoint of the arc. M is on, so O is the midpoint, L is the intersection of XZ with YO. That's L. M is on KL. OK is the altitude from Y to AB. Right. This is K. And then O is the midpoint of AB. L. M is on KL with MA is equal to MB. Okay, so it's the intersection of this with KL. I think that looks a little better. This is M. Let's hide some things. And I is the reflection of O across XZ. So it looks like, is it obvious that I lies on that? Let me move things around, see if that's, no, that's not necessarily true. Okay, that's I. Prove that if XKOZ is cyclic, then so is YOMI. So right now it's pretty clear that YOMI is not cyclic. So let's move things around a little bit. So something like that, but let's make it look a little better. So there's got to be a way, like I feel like if we do something like this, like I feel that looks a little better. I have to shrink it a little bit, but yeah, I think that's a okay diagram. So yeah, maybe I could even make it a little bit bigger, but just hide the bottom part of this circle. So something like that.
You can draw this diagram perfectly.
Okay.
You just take X and Z and then intersect circle XOZ with AB.
Yeah, so basically I could just let Z be the intersection of that circle with the other circle. So
you can do it like that also.
But yeah, I see what you're saying. Yeah, you were doing X and Z first, and then defining y, and I'm doing x and y, and I'm defining z. So, okay, so actually, I probably could have just gone into the algebra and like redefined stuff, but it's okay. So L is the intersection of XC with YO, and then M it's on this perpendicular bisector. And then we draw KL. So this is M. And then we reflect O across XC. Then we get I. Let me make I a little bit farther away. Circle. That. And we want to show YOMI is cyclic. So yeah, this looks maybe a little easier than I thought it was originally, but so OX, so OX, so this is a rhombus actually, XOZI. It doesn't have to be a rectangle, it almost looks like a rectangle there, but it's a rhombus. I think that's a good picture. All right. I don't think Mi and X are collinear, right? Oh, it looks like they are. Okay. Oh no, not necessarily. It's just the way I drew it. But yeah, Mi and X are not necessarily collinear. You can see it right there.
If you intersect X, Z, and AB, then you would get a harmonic quadrilateral. I mean, bundle. Yeah.
All right.
That is something we can prove. So yeah, A, B, C, and K, they are harmonic.
All right. So yeah, that's equivalent to saying BX and AZ intersect on YZ, right? Or maybe you thought about it.
Yeah, then you would be done by Severman laws.
Then what?
Then like we can use Severman laws if they are concurrent at YZ.
Yeah. But how did you think about it, Stefan? Like I don't.
Yeah, I mean, it is not completely obvious. You have to use a lemma about harmonic bundles. So let's say that C, K, A, and B are harmonic. Then a well-known lemma is that CK times CO is CA times CB.
Yes.
And you can kind of do it in reverse because of
Yeah. It was in ABG. Yes. It was in Stephen's work of geometry.
And yeah, another thing I noticed is that CY is the tangent, but yeah, that is obvious because of the harmonic bundle thing, because then YK should be the polar of C.
Okay. Yeah, because YK is perpendicular to CO. That makes sense.
Hmm.
Yeah, C, K, O, and B. So yeah, if we know they're harmonic, yeah, we could draw AZ and BX. But yeah, let's first see. See, I don't know if that would be useful. It almost looks like, I mean, it's probably not an angle bisector, but yeah. So yeah, is there some other point on this that might be useful? Oh, what?
So since L lies on the intersection of Y, O, and KM, so we can consider a point, let's say J. Have we used J in here? No. Such that it's parallel to OB.
Okay.
Yeah.
Through L.
And no. So such that OM, sorry, JM is parallel to OB at the same time. At the same time, JO is parallel to YC.
YC. Okay.
Yeah, so we'll have homothetic triangles.
Okay. So J is like on the right side over there. Okay. So
Yeah.
so that would be J over there.
Yeah. So my diagram is a little bit different, but yeah.
Okay.
Then by homothety, J lies on XZ.
Sorry, how?
J lies on line XZ because of the homothety.
XZ. Ah, yes, right.
All right. And would J also, I don't know if this is true, but maybe J lies on this circle? No.
Is J the radical center for all these three circles if YOMI is cyclic?
Is J what? The radical center?
Yeah. No.
I don't think so, because the radical center.
Yeah, it's not. It's not.
Okay.
Can you keep the circle?
Yeah, sure.
Yeah. And can you show us the center of the circle?
Yes.
No, I thought it's no, no, we didn't know.
So yeah, the center of the circle, it looks like it's the midpoint of CJ. So it looks like, is that right?
I don't know. I'll drop it in.
Yeah, can you try more? Yeah, yeah.
Yes, so it looks like, but I don't think COJM is a parallelogram. But yeah, it looks like it's the midpoint of CJ.
Can you mark down the midpoint to confirm?
Just to check it.
Yeah, yeah.
Yeah. So yeah, somehow the midpoint of CJ is actually the center of this circle that we're trying to show.
Actually, I thought it was going to be on OZ, but that this would be even better.
Yeah. So we know the midpoint of CJ is going to be equidistant from M and O.
Also, it is obvious that the center of that circle is on XZ. That is because OI, I is the reflection of O in XZ.
Oh. So yeah, we know that we know that D is the circumcenter of MIO, and we just need to show that Y also lies on that circle.
How about we do a little inversion?
Okay.
Inversion with a center O.
I think inversion will make it even harder.
Because let's say x and the tangent from x and z is let's is ik, and the tangent from x and z is intersect at one point. Yeah, and ik, yeah. Yeah, so the inversion will make will transfer K to C, L to OI, cut that circle.
Right.
Yeah. I will be the midpoint of EO. Yeah. I will be the midpoint of EO.
So that would be the diameter of the circle.
Yeah, midpoint of EO, and M is will be the intersection of the circle OFC, cut OM.
OFC.
Yeah, cut OM. Yeah, so we need to prove that G and H are collinear.
F, G, and H are collinear.
Yeah.
That doesn't look true that F, G, and H are collinear.
Hold up.
Okay. Maybe Y, G, and H.
Yeah, Y. F, G, and Y. Because O, Y, I, M is cyclic. So after inversion, they must be collinear.
Okay.
Yeah.
All right. So we have kind of two different ways. So yeah, hey Johannes, thanks for joining.
Hello.
Okay, I'm not exactly sure. I didn't pay attention to the inversion thing. But I will just say some stuff I found about the point D in this picture.
Okay.
Yeah.
So I proved that D is the circumcenter of DIM.
D is the circumcenter
Of
what?
OIM, sorry, OIM.
Oh yeah. So we can prove that because yeah, we know since D is the midpoint of CJ, DM equals DO,
Yeah.
and then
Yeah.
their function. Yeah.
So we just need to show that DL is DM, for example.
DL equals DM or what?
Yeah.
But DL, because L is not on the circle, so DL doesn't equal DM.
Oh, DY actually, yeah.
DY, yeah.
Yeah.
So
Yes, so I agree with that. If we could show
So-
DY equals DM, that would solve it.
So can we consider it like this one is the center of yeah, it's the circumcenter of triangle YOM, and since I is the reflection on the line that is yeah, so it's OI is perpendicular to JC, so it implies that I lies on this circle.
But if we take the circumcenter of YOM, I think that's what you're saying, right?
Yeah, YOM, and since I is a reflection, so it's equidistant from D.
But the thing is, we wouldn't know that that center lies on CJ. So we could take the circumcenter of YOM, but then we'd have to prove that it lies on CJ. And if we don't know that, then we don't know necessarily that if you reflect O over it, that it would give you a cyclic quadrilateral.
Sorry for interrupting, but I think I solved the problem.
Okay.
The one thing we were missing is midpoint of OC.
Okay.
So if you join the midpoint of OC, then that midpoint is obviously equidistant to O and Y. That is because we have that angle Y is 90. CYO is 90.
Yeah.
So we would need to show that D is also be equidistant, but ND is parallel to OJ, right?
ND is parallel to OJ.
Yeah, that's together midpoint theorem.
Because they're
and yeah,
both midpoints, yeah.
And because OJ is parallel to CY, then we have that OJ is perpendicular to OY.
Yeah, that solves the problem.
Yeah.
So we didn't even really, did we need that anything about harmonic conjugates? It almost seems like we solved it.
I think we need it because I used that angle CYO is 90, and that is because of the harmonic bundles.
Okay, yeah, you're right. Okay, so yeah, inversion probably would have worked also, but this does it. So I'm just gonna hide this stuff for now. Yeah, I'm sure there was a way to do it with those points.
It's interesting how point J on the surface doesn't look too useful, but it actually solves the problem.
Yeah, it's very interesting. So this circle, let's see, I think I can delete that circle.
You can also delete the point C and F.
The point what?
I'm saying like you can also delete the point E and F, right?
Yeah. All right. So I'm gonna type it up. Let me see how I should make space for the solution. Because yeah, this is like a wide diagram. How do I make J a little closer? We can make this taller. And yeah, I think that might be good. So yeah, that looks like it should give us a good amount of room. Okay, so label. So okay, first of all, let XZ intersect AB at C. C. Then we are saying, so A, B, K, and C are harmonic. Because so C,
Like the circle with radius square root cx into cz sends k to O and A to B. So basically, they are harmonic bundles CKAB.
yeah, so CK times CO is CX times CZ equals CA times CB. So so that means that AB by a well-known lemma and then that implies that YK is the polar of C. That means that CY is perpendicular to OY. Yeah. So let XZ. So let the parallel through M to AB meet XZ at J. All right. And then by a homothety, CXZ and J are collinear. So wait, that homothety, that's a homothety at L, right? Wait, let me think about that. So is that we're saying a homothety at L takes YKL to MOL? Let me think about that. So wait, how did we define L? So L is the intersection of XZ with YO. How did we know that?
L is already defined.
Yeah. How did we know that ML and K? Oh, M is on KL by definition. Okay. So basically a homothety about L. So yeah, by a homothety at L, J, L, and C are collinear. So all right. And then so we let D So yeah, first we kind of define let D be the midpoint of CJ. Then DO equals DM. Equals DI. I think that's what we saw. Or I'll say DM equals DO. And then that's DI. By definition, because and then we use point N. So let N be the midpoint of CO. And then NZ is parallel to OJ. I'll put this down here because I think it might be easier. So NZ is parallel to OJ.
ND actually. Like ND is parallel to OJ, right?
MD and I was gonna say
ND.
So because N is the midpoint of CO and D is the midpoint of CJ. So ND is parallel to OJ. And we have NY. Okay, so we have NY equals NO. That's because CYO is a right triangle. So NY equals NO, and we wanted to show that DY equals DO. But ND is parallel to OJ, means that basically,
I mean, you can take a homothety at KD intersection YO, sending like K to D, proving that DY is equal to DO.
so sorry, hold on just one sec. So
can I repeat what I said?
So basically, if ND is parallel to OJ, then that means ND is perpendicular to OY. So and that would solve the problems because so I'm going to switch these two. So NY equals NO. So these two together mean that so if ND is perpendicular to OY, then that means DY equals DO. DO, that means D. So we have DY equals DO equals DI equals DM. And that means that YOMI is cyclic. So yeah, this problem didn't really use any sort of super advanced stacks. Yeah, the key was finding that point B and finding the harmonic division. All right, so let's see what time it is. It's 11:10, so we have about 50 minutes left. So yeah, this one I think is pretty hard actually. I think. You could take a look at it. So let me see. Who's still on? So we have a triangle with circumcenter O and orthocenter H. So I'm going to use my tool to draw. I think it's hard because I think it was like, I don't know if it was problem 3 or problem 6.
So I've solved this one, and I don't think we can do it in 50 minutes.
Okay, you think it's pretty hard?
Yeah, it took me 2 hours.
I'm just going to draw it. I'm just curious. So I just want to see what it looks like. So yeah, I mean, N is the 9-point center. Right? So I probably don't even need to draw. Well, I do need to draw this because it's used later. So N is the midpoint of OH, so that's the 9-point center. So it's probably worth drawing a 9-point circle. But basically, we draw the tangents to all 3 of them. So what's the name of this triangle formed by the 3 tangents? Is there a name for it?
Tangential triangle.
Tangential triangle.
Yeah.
So draw it like that. So yeah, maybe something like this. And the line through H, so we draw AN, BN, and CN. And so we draw the line through H perpendicular to those 3. So we'd get like 3 triangles, and then we'd want to look at their circumcircles. So CN and then BN. Yeah, this looks kind of hard. So we would have this circle. So I didn't draw that difficult. Let me draw these points in. This, and that point. And then this. It's going to be hard to draw these. This and this. And then I'm guessing this and this. And then this and that. So then we'd have this, this, and this, and then this, and G, I think S and R, and then J, P, and Q. Something didn't happen right.
Yeah.
The common chords just be concurrent on line OH. Oh, I could be. It's not saying they're coaxial. It's saying that the
Radical center.
Yeah.
Yeah. So yeah, that's how.
I think we can do this.
Are you sure? It seems complicated to me.
No, I
Yeah,
don't
it
think
kind of looks fun.
like my solution was 4 pages. The official solution was 3 pages.
What do you think, Stefan? You want to try something else?
Was it synthetic or bash? I'm
We
like
can do it.
hard
We
problem.
can do it next week, but we must start with it.
Okay. So it takes a long time. Let's try this one. So
Actually, if you want, 2020 USA TST problem 2 is nice. If you haven't solved it.
I'd let's see. So USA TST.
Yeah. Problem 2. 2022. 2020.
All right. We've probably done it. Yeah, it does look kind of.
I mean, like 2016 USA TST 2 is also good if you guys have done this problem.
Let's see. So I'm going to, let's take a look at this one.
If you have solved it, I have another suggestion. If you have solved it. Yeah.
I probably don't remember though. So let's see.
Yeah, so for to be 100% sure that you haven't solved it, I have one that I'm pretty sure that you haven't solved.
But yeah, I probably don't remember the solution even if I did solve it. So I think it's a good problem. So yeah, let's just take a look at this. Let's see. So I kind of like common external tangents like that.
Yeah.
So I feel like there's not that many problems with it, but it's often interesting. Okay, so we have common external tangents that meet at T. And then we want it to, this should be A, and this should be B. A circle through A and B, it intersects the first circle again at C, another at D. So this would be D, this would be C. Oh, I think we showed that E, C, and D are collinear. Is that true? I think I remember some kind of problem where we show that T, C, and D are collinear. Because TA times TB, you can kind of write that in terms of TA1 and TC1.
You can do an inversion.
You can do an inversion.
Which sends one circle to the other, and that's it.
Oh, okay. So is this problem trivial? I didn't read the rest of it. So AC and BD meet at X, and AD and BC meet at Y. AC and BD meet at X. Wait, that doesn't sound right. AD and BC meet at Y, and AC and BD meet at X. But then, did I draw something wrong? Maybe I swapped C and D. So,
But yeah, I think we solved this problem in some other session.
okay, so let's try a different one.
So 2018 IMO SL G7. It's also nice. If you want, if you want another one, I have another one, G5.
I did both of those.
Okay, so
What
yeah.
about G5 2018?
Let's see. So do we want to do this one or the one that you just said? Oh, can you guys, do we want to do the one from Evan Chen that you just sent, or?
Which one?
Yeah, I think so. Sorry, it popped up in Microsoft Edge, so I think maybe that's why you can't see it. But this.
I have a very, very nice problem, and I don't think anyone have solved it.
Okay.
It's from I forgot the year. Alhamdulillah. It's from IGO. I'll just check the year. Just a second. I think it's 2021.
Have you solved this one yet? So IGO 2021. We did IGO on another session. Like, yeah, that's the thing. I feel like we're going through most contests more than once, which I feel like is okay if we don't really remember solutions, but I kind of like this problem. You want to just try this one?
I don't know. Ask the others.
Okay.
So
There is
I
a
think
high chance I did that IGO 2021 problem.
problem 5.
I did a part of it, but yeah, it is a great problem. It is really beautiful. The part I did is proving that centroid lies on AD, and I posted that on AOPS. But yeah, I didn't prove the
Yeah, it's
whole
the
problem.
one about the Euler line.
Yeah, yeah.
2022.
Just a second. I'll check there in a matter of seconds.
Okay.
It's 2021.
Yeah, 21.
Oh, 21. Okay.
Next session, I have a lot of problems that are nice, but they would take time.
Okay.
Yeah.
2021.
Yeah.
Advanced, you said?
Yeah.
Is it problem 5?
Yes.
But that's 2020.
That's 2020.
2020, sorry. 2021 advanced P5, this one.
Yes.
Okay.
Needed. Yes, this one. So everyone wants to try it.
All right. Let's try it. Interesting. Okay, so we want to show both A and B lie on the Euler line of this triangle. We draw this. So PAB equals BCA. So basically that would mean we would have some kind of, right, like AC would be tangent to a circle through A and B. So basically what we could do, so we want to draw a circle center on this line that's tangent to AC. So basically we could do it like this. Is that right? So this would be P. No, that's not right. PAB.
To be honest, I think this would take us more than 40 minutes, 35 actually that we have.
Oh, really?
Yeah.
Wait, have you already solved it?
I haven't actually solved the full problem, but part of it.
It's hard. Yeah.
Yeah.
So you want to try something else? Okay.
I think we should just go back on that problem.
This one?
Not. I mean, we could do that. It doesn't look hard. But the other one with the radical center.
Okay.
But yeah, it's better to just do an easier problem. So not the radical center, not the IGO. So something.
Maybe this.
Stefan, you have a doubt.
You want to try this one?
We can try it like that one chain problem, because like that will not take much time actually.
And
And it's also good. Yeah, the one I sent in chat.
Okay.
Sorry, I made you jump a lot from problem to problem a lot.
No, there's no problem.
All right. Okay. So the TSTST 2016, right?
Yeah, I've sent the AOP string on chat. You can check.
Okay.
Let me send it again, actually.
I think I got it. So this one, right?
Yeah, this one.
All right. Okay. Let's delete that. So this will be H. This will be O.
Basically, G is the AQ point.
Okay. So M and N, I'll draw those. So yeah, G is the Q point. So basically it's collinear. Yeah, we might as well just do this. So this is M. We might as well call this something. I'll just call it P, or we already have a P. So we'll call it R. And N is the midpoint of AH. Yeah, this altitude tool has been really helpful. Or orthocenter tool. So let's see. More problems. Okay. So it meets the line AN. I don't get this. Wait, the circle diameter AH meets. Oh, N is, I swapped these two. So N is the midpoint of BC. And this is M. Oops, not that. And then that's Q. Obviously, AQH is 90. And then we draw the tangent at G. So NF and NE are tangent to the circle. We know that. That's well known. This meets OM at P. So OM is going to be the perpendicular bisector of AG. So this is P. Okay. I mean, P is really just the intersection of the tangents at A and G, right?
Yeah, we can ignore P in that way then.
And we want to show that the circumcircles of G, N, Q. Oh yeah, so P, yeah, P we don't really need point P. So we have G, N, Q, and MBC. Intersect on PN.
Okay, can you like introduce AG intersection BC and this 9-point circle?
AG and BC.
Yeah. Because
Yeah.
like radical axis.
They'll intersect on the circle. These two.
Yes.
And then, yeah, maybe we'll even want to intersect the F with BC. That's the polar of P. Okay, so basically we want, I mean, it's the same as showing that, oh, I was going to say Pn is the radical axis, but that's not true. So yeah, let's look at this intersection point. J. So we could call it T or T prime.
Wait, can you like introduce the 9-point circle as well? Because like M lies on the 9-point circle, and so does P here.
Yes. Oh, and it looks like T prime lies.
Yeah.
Interesting.
I think we should invert it N with radius NB.
N with radius NP.
NB.
NB.
Yeah, then Q goes to A, and yeah, AEF is fixed. I goes to D, and yeah, 9-point circle goes to EF, line EF. And
Yeah,
we
it does look
need to
good.
think about where P goes.
Okay. Is it obvious that these three concur at the same at a
Wait,
point?
is P T dash and N collinear?
Is what?
P T dash and N. The concurrence point or the circle. Yeah, they are. So like we can find a way to replace P by T dash if we prove that these three circles are concurrent, and
Well,
then
that's
basically
okay. You're saying if we prove these are concurrent, then
and then prove the collinearity, then which is just I guess angle chasing by after that.
okay.
So I guess we can replace P by T dash.
Replace P by T dash or
T dash, because like T dash gives very nice conditions actually.
yeah.
P is not a nice thing actually.
Okay.
I just want to say that I can prove that T prime lies on the 9-point circle.
Okay.
I mean, T is, it depends how we define. Let's say T prime is the intersection of those two circles, and then T prime lies on the 9-point circle.
Okay.
So if we inverted, we did that inversion, which I just said before. Point M goes to the midpoint of EF.
Okay.
And B and C stay the same. So, and also circle, the other circle, INQJG, that circle, it goes to line AD.
Okay.
So that means that T prime goes to the intersection of AD and the circle BJC.
BJC.
Yeah. That makes sense, right?
So B and C are fixed, M goes to J. Yeah, so it would be the intersection of BJC with AD. So like this point right there.
Yeah, and I can prove that that intersection is exactly that point. The intersection of AD and EF lies on that circle BJC.
Okay.
So it is well known and kind of obvious that EF and I are collinear. For example,
yes.
the radical axis.
Yes.
And we define K as the intersection of AD and EF.
Okay.
Then we have that IK, E, and F are harmonic.
Yeah.
And J is the midpoint. So again, we can use the lemma I talked before in the session to prove, because of that, we have that IK times IJ is IF times IE.
Which is IB times IC.
Yeah.
That proves that K lies on the circle. So, and then the inversion proves
That T prime lies on the 9-point circle. Yeah.
That's a great proof, actually.
okay. So then we just need to show that is this, yeah, maybe it's the radical axis theorem. We just need to show that P, T prime, and N are collinear. Do we know that T prime, K, and N are collinear?
Yeah, because of the inversion.
Okay.
And yeah, that is probably useful.
So yeah, I wonder if there's a way where, yeah, we can use the radical axis theorem somehow. This circle, I just don't know the other circle.
You can use the radical axis theorem on like 9-point circle, and then like this GTJL circle.
Yeah, these two, right?
Yeah.
And then, yeah, the other circle, I'm not sure what it would be.
Yeah.
I have an idea. We have to show that Pn is the polar of I, right?
Yes.
Okay, so K lies in the polar because I, K, F, and E are harmonic.
So yeah, K lies on the polar.
P lies on the polar because Lahira's theorem, and N lies on the polar because NE and NF are tangent. So that's it.
So N lies on the polar because
And NE and NF are tangents.
so K, N, and T. So line T prime K N is the polar of I, right?
Well, T prime K and N are collinear. That's what we know already. And then we show that Kn and P are collinear, and because they all are on the polar.
Yeah. And then
So
showing
that solves the problem.
how do we know? Oh, and we know P's on the polar of I because I's on the polar of P. So yeah. Yeah, this is just one big polar bash. Yeah, we solved it super fast.
And you can you don't need T prime, it is just T.
T. Yeah. Well, I was thinking if I call it T, but yeah, I can just call it T. So, you guys want me to type this up, or I could probably do it quick.
I mean, we only have 20 minutes left now.
Okay. You want to try this one?
I mean, we can try that IITB Marathon one because that one seems easy.
Okay. So I is in the center. Oh, actually, you know what? Let's do this. Whoops. I don't mean to do that. Ready. So yeah, basically we draw the midpoints of the arcs. Just label them right. So this should be F. Then we draw IEF. So AFIE is a kite, right? And so is BFIB and CEIB. So I don't know if that helps with this at all. Basically,
This is almost trivial. This
oh,
problem.
really?
Yeah. So you don't need ABC. You
Yeah.
just have D and F and the orthocenter I.
Okay, so DEF is orthocenter I.
Yeah. And then those circumcenters are just reflections of O in lines EF, D, and DF.
And so DM.
So you can just, for example, see that those three lines concur on the 9-point center.
So oh, I thought maybe it would be the center. So if you reflect the circumcenter over EF and then you connect it to D, so that line contains the 9-point center.
Yeah, that's because what is the name of that point?
Cosnita or something, or
That on the top, the
Humpty point, Dumpty point.
no, literally, what is the name? Because I can't see because the text.
This point up here.
Yeah.
J.
So basically, NJ is equal to DI. That is a well-known lemma.
Yeah.
And because of that, DJ bisects NI, and that's it.
So it's the midpoint of OI. So that's not the 9-point center, that's the midpoint of OI, right?
Well, it is, but
What's the 9-point
you can
center
just
of
throw
DEF?
away
Yeah.
triangle ABC.
So DEF is the 9-point center. Yeah. That's too easy.
Yeah.
Can I try this one? Let's see.
Let's do it.
Okay. So we have an equilateral hexagon. So we could kind of draw it like this. So we could start with just a triangle and then pick a length and then just use the compass tool a bunch of times. So okay, we just need these to intersect. So make this bigger, like that. So we have something like this. Maybe it's even worth keeping the circles for now. But I think are all equilateral hexagons like drawn this way? I think so, right?
Well, we don't need to draw every equilateral hexagon. We just need one example for our picture.
But can any one be done be like, yeah, I guess they would all be like this. So
But yeah, they probably are.
because I guess, yeah, I didn't want this one to have like a special property they don't have in general. Okay, so let me hide that point. So O1 is the circumcenter of A1, B1, C1. Okay, so O1 and H1. So and then we draw O2 and H2. So let me hide these circles. O1, O2. Might as well draw this triangle. And then H1 and H2. Is that always true that they're like congruent like this? Is that obvious? Or are they congruent? I think so. Well, then it might just be some kind of homothety, right? If they're congruent.
I think they're not.
They're not. So oh yeah, because here you can see it's not parallel anymore. Yeah. Okay. So H1 and H2. Trying to make it so that it's hard to draw a figure here, but I feel like that looks maybe a little better. So H1 and H2. To be H2. See it. So yeah, he already left, but this is H1. And we want to show O1, O2, and H1, H2 are either parallel or coincide. So yeah, this is an interesting shape. But okay. I mean, obviously O and O2 is perpendicular to this segment. Maybe we could show the difference of powers. So like we call this X and Y.
It looks like those 4 points make a parallelogram.
Okay. Interesting. Yeah, I could check it.
Oh, that's actually not true. That
Yeah, it's pretty close, but so yeah, let's draw a parallel line. Let's see. So yeah, definitely parallel. Let me just make sure they're not actually similar. I don't think they are. No. So basically we're saying they have the same 9-point center. Those two, if that's a parallelogram, yeah, that means they have the same 9-point center.
yeah, but it is not a parallelogram.
Oh, it's not, okay,
Yeah, yeah. I made a mistake there.
sorry. Yeah, it's really hard to draw a good figure. I kind of like this problem. So we have a line. I feel like there's a lot of lemmas about having two different orthocenters and two different triangles, right? I just don't remember them. There's something like some kind of double orthocenter lemma. Let's see. Yeah, even though it's not a parallelogram, I wonder if we could say something about the 9-point centers of those circles. one 9-point circle. Yeah, it's an interesting problem. So obviously this bisects that angle, or sorry. So C201 bisects that angle, and A201 bisects that angle, and B201 bisects that angle. So it's weird. And then these bisect these angles. Do we have isogonal lines somehow? Let's check. No. Maybe, let me check if these are equal. So we have this, it's 3.48 degrees. And this, no. We have 2 more minutes left. Let's see. Yeah, I'm gonna Google after the session double orthostat lemma. Let's see, I think I might apply here. All right, I think it's. Or I'm sorry. Go ahead.
Yeah, probably much more work to do, but you can just notice that xy is perpendicular to O1, O2. So we can kind of get rid of O1 and O2, and we would want to prove that H1, H2 is perpendicular to xy.
Yeah, but how would we use? I guess we would just know that these are equal. Yeah, like you don't need O1 and O2. I guess you just know that these are equal and so on.
Yeah, that is just a very brief idea, which I don't know if it actually works. But yeah, this problem is a bit harder than some other problems we did.
Yeah, looks tricky. But although I think it might have been like a number 1 or a number 3. I'm not 100% sure, but let's see.
Number 3 and number 1 are, I think, a big difference.
Oh no, I thought it was maybe a number 4 or a number 1, but I might be wrong though. I don't know why.
If it's number 1 or number 4, then it probably has an easy solution.
Yeah. So let's see what number it is. Oh, it is a number 1. So yeah.
Yeah, then probably it isn't too hard.
But yeah.
We just needed a bit of more time, but yeah, we don't have it.
It's all right. So yeah, thanks for participating on the session. And for everyone watching on YouTube, thanks for watching. So if you want to join us in the future, we meet every Sunday at 8 a.m. US Central Time. So my email is mgreenb801@gmail.com. It's in the description of my video. So again, we meet every Sunday at 8 a.m. Central Time. So thanks again for watching and have a great day. See you next time.